Hello students, today we will start with a common topic of JEE Main, Advanced and NEET, that is molecular orbital theory, which is important subtopic of chemical bonding. Electrons present in atomic orbitals. As we know, electrons are present in atomic orbital. Each and every electron has wave and particle nature. Electron has two types of nature, wave nature and particle nature. So the wave function of the electron is denoted by a symbol that is called psi. Here we can denote the symbol as psi. We can write the symbol as this psi, and the spelling of psi is psi, where p is silent. Okay, so this is the symbol for wave function. So electron present in atomic orbital, and atomic orbital will combine two atomic orbital of two atoms combine, say hydrogen. One atom is hydrogen, the other atom is hydrogen. So when they will combine, they will form molecular orbital, and electrons present in atomic orbital, same electron also present in molecular orbital. If there are, say, one atom having wave function psi a, this is atom A, electron of atom A denoted by psi A. Electron of atom B denoted by psi B. Okay. When these two wave function combine constructively, it is called constructive interference or addition of wave function. Here, due to addition of wave function, see this amplitude A and this amplitude A becomes double here. So there is addition of wave function. Both are in phase. In phase means both are in the positive direction. Both waves are in positive direction. So it is in phase wave function. So when it is combined, the waves are added, and this is result into formation of bonding molecular orbital, which is called BMO. BMO stands for bonding molecular orbital. These are addition of two wave function, and it forms sigma, pi and delta bond. So addition of wave function always forms sigma, pi and delta bond, and subtraction of wave function, the other one. This is destructive interference of wave function. Here this is in phase and this is out of phase. This wave is in phase and this wave is out of phase. When there is destructive interference, means there is subtraction of wave function, it is denoted by psi A BMO and psi A and minus psi B. Here the amplitude is less than the original amplitude. Whatever we had added, it is less than that. Here it is doubled because it is constructive interference, but here it is less than the original one. Hence, this is called antibonding molecular orbital, subtraction of wave function, and it forms either sigma star orbital or pi star antibonding orbital or delta star antibonding orbital. Any of these three depending on the type of overlap. If it is overlap of, say, px then it is sigma. If it is py lateral overlap, then it is pi. If it is d orbital, it is a new type of bond. You might not heard about this bond. This is called delta bond. Delta bond is always formed by d orbitals. So any type of molecules always formed by combinations of atomic orbitals, and atomic orbitals have electrons. Electron has wave nature and wave function of electron. When combined, there are two ways. One is forming addition. By addition of wave function, it forms bonding molecular orbital. By subtraction of wave function, it forms antibonding molecular orbital. So this way, the wave function of two atoms combine and they form either bonding molecular orbital or antibonding molecular orbital. Next, we will see the bonding molecular orbitals is energy wise how it will form and where it lie. See, when there is bonding molecular orbital, it will always lie in the lower side because energy decreases when stability increases. So in the next part we will see the position of this bonding molecular orbital and antibonding molecular orbital in the molecular orbital diagram or MO diagram. So here I will write MO diagram or molecular orbital diagram. Similarly, another name for this is energy level diagram, because it denotes energy level diagram. Okay, so here if it is like this, energy levels I can denote like this. Okay, so this is a atomic orbital, this is another atomic orbital having some electrons, say one electron here, one electron here. So there are two types of molecular orbital. One is bonding molecular orbital and the other one is anti-bonding molecular orbital. This is ABMO and this is BMO. Okay, this is sigma 1s, this is sigma star 1s. If I consider this as 1s orbitals, so these are the molecular orbital, possible molecular orbital formed by combinations of these two. If there are two electrons in this, here also there are two electrons. Okay, there is no electron over here in the anti-bonding, and here there is. So I can denote this part as atomic orbitals, this as atomic orbitals, whatever atom. If this is hydrogen, I will write hydrogen. If this is helium, I will write helium. Okay, since it is one, I can write hydrogen over here. Atomic orbitals of hydrogen here, atomic orbitals of hydrogen here. I can write like this, and this is called molecular orbitals of H2. Okay, so this way I can denote, I can draw the energy axis here. This is energy level diagram or molecular orbital diagram of any type of atom. I can write this way, since this denotes the energy level of atomic orbital, this denotes energy level of molecular orbital. For bonding molecular orbital, the energy is less. Okay. Stability increases. This is more stable. For anti-bonding molecular orbital, stability is more. Stability is less. Energy is more. If energy is more, there is always less stability. If energy is less, always more stability. Okay. So two types of atomic orbital formed by this combinations and the destructive interference and constructive interference of wave function, and sigma 1s, sigma star 1s, the simple types of atomic orbitals. For hydrogen atom, I can write like this. And in entrance exam part, if I will go, they will ask what is H2 plus, what is H2 minus bond order, what is H2, it is denoted here. But H2 plus and H2 minus, these are formed by removing electrons from this. If I will remove one electron, it will become H2 plus. If I add one electron, this will become H2 minus. So I can write the bond order and I can arrange them in the increasing order of bond length. Say for example, for H2 I can write the bond order. Bond order formula is, you all know that bond order is number of bonding electron minus number of anti-bonding electron divided by 2. So bonding electron here is 2, anti-bonding electron 0, that is 1. So 2 by 2, it is 1. So there is only one bond between hydrogen and hydrogen. This is given by the bond order formula, and molecular orbital diagram explain the same. Similarly, H2 plus, if H2 plus is there, one electron gone, so there is only one electron. So for H2 plus I can write the bond order as H2 plus. Bond order I will write like this. See, I will deduct this electron. I will remove this electron. What happens? There is only one electron, minus 0, no electron over here, and 2. So it becomes half, which is 0.5. Okay. Similarly, if it is H2 minus, so I will add one electron. I will already, this is H2, and I will add extra electron to H2. So the bond order over here is what? What is the bond order over here? 2 minus 1, bonding minus anti-bonding divided by 2. Bonding minus anti-bonding divided by 2 is called H2 minus bond order, that is 2 minus 1 by 2, that is 1 by 2. Again it is 0.5. So whether it is bonding or anti-bonding, we will see the bond order. Okay, see here the bond order is 0.5, here it is 0.5, here it is 1. So two bond order are same and one is less than that. Means bond order of hydrogen is more and bond order of H2 plus and H2 minus both are less. Okay, so if the question is arrange the species in the bond length order of bond length, then I can easily write H2 is less than H2 plus and less than H2 minus, and this is having high bond order as compared to this. Okay, the bond length of H2 minus is always high because see here we cannot compare with the bond order is same, but bond length wise I can say this one, the H2 plus H2 minus, if I compare these two, since the number of anti-bonding electron increases, bond length increases. Remember, in case of H2 minus there is one extra electron present in anti-bonding orbitals, so that's why the bond length of H2 minus increases because number of electron in the anti-bonding increases in case of H2 minus. There is no electron in case of H2 plus, no electron in case of H2. Similarly, I can predict the magnetic nature of this species H2. All electrons are paired. There is no electron over here in H2, so all electrons are paired. In case of H2 plus and H2 minus, say H2 plus there is one unpaired electron and in H2 minus there is one extra unpaired electron here. So H2 minus and H2 plus, they are paramagnetic, whereas H2 is diamagnetic. The magnetic moment is zero. They are not attracted by any types of magnetic field, and H2 plus H2 minus paramagnetic, they are little bit attracted by the magnetic field. Magnetic moment is not zero. So H2 plus H2 minus paramagnetic, bond order is same, but bond length of H2 plus is less than that of H2 minus, and bond order of H2 plus is equal to H2 minus, but bond length of H2 plus is less than that of H2 minus, and H2 is having less bond length than both the species. Okay, this way we can easily explain the stability, the bond length, the bond order, the magnetic nature of all these species with the help of the advanced theory in chemical bonding, that is molecular orbital theory and MO diagram. So this is an important question for this type of entrance exam like JEE and NEET. So they can ask this H2 plus, H2 minus and H2, the order of bond length or bond order or magnetic nature. Any questions based on this can be asked. So prepare with this. Thank you. Thank you.